Today, we're pulling back the curtain on one of the most powerful technologies shaping our world, machine learning. I mean, it's the engine behind everything from your Netflix recommendations to huge scientific discoveries. But what is it, really? Let's get into it.
Okay, so first things first, let's clear up something that trips almost everyone up. You hear AI and ML thrown around constantly, sometimes in the same sentence. So are they the same thing? The short answer, nope, not even close.
The trick is to think about their relationship. They aren't twins, they're more like Russian nesting dolls. One fits neatly inside the other.
And this is exactly how it breaks down. At the very top, you've got artificial intelligence, this big, broad idea of any machine that can mimic human smarts. Tucked inside of that is machine learning, which is a specific way to achieve AI by learning from data. And then, inside that, you have deep learning, which is a really specialized type of ML. So here's the key takeaway. All machine learning is AI, but not all AI is machine learning.
All right, here's our game plan. We're going to cut through the buzzwords, then talk about the most crucial piece of the puzzle, data. After that, we'll look at the three main ways machines learn, peek inside the toolbox they use, see how it all gets put into practice, and finally connect all these dots to the AI that's making headlines right now.
All right, Section 1, Beyond the Buzzwords. Let's nail down what we actually mean when we say a machine learns.
You know, this definition is from way back in 1959, from an AI pioneer named Arthur Samuel, and it absolutely nails it. The magic words here are without explicitly being programmed. See, in old-school programming, you had to write a rule for everything. If this happens, then do that. But with ML, you don't. You just show the computer a ton of examples, and it figures out the rules all by itself. It learns from experience.
Section 2, Data, the raw ingredient. Now, if there's one thing you take away from this, it's this. You can't understand machine learning without understanding data. Seriously. It's the fuel, it's the textbook, it's the teacher, it's everything. And how we use that data changes everything about how the machine learns. And that really comes down to this one big difference. On one side, you've got labeled data. Think of this like a practice exam that comes with an answer key. The machine sees the question, we call those features, and it also sees the correct answer, the label. On the other side, you've got unlabeled data. This is like being handed the exam with no answer key. It's just a pile of raw information, and it's up to the machine to find any meaning in it. Here's a super clear example. Let's say we're building a spam filter. With labeled data, the machine sees the features, the subject line, who sent it, if there's a link, but crucially, it also sees that label column. It knows for a fact that the first email is spam and the others are not spam. It learns by connecting the dots between the features and that known answer.
And now, boom, the answer key is gone. It's the exact same information, but without that label column. It's unlabeled. The machine has to look at the patterns on its own, with no answers to guide it. This single distinction is the key to, well, pretty much everything that comes next.
Section 3, Three Ways Machines Learn. So, based on whether we have that answer key or not, machine learning basically splits into three main approaches.
First up, the most common one you'll run into is supervised learning. This is where you use that nice, clean, labeled data, the stuff with the answer key. The whole goal is to get the model so good at the practice test that when it sees a brand new question, it can predict the right answer all by itself.
Next up is unsupervised learning. This is what you use when you've just got a massive pile of unlabeled data. There's no right answer to predict. Instead, the model acts like a detective, digging through the data to find hidden patterns or natural groupings, like sorting your customers into different types based on what they buy, even if you never told it what types to look for.
And number 3 is reinforcement learning. Now, this is a whole different ball game. It's not really about data sets. It's about learning by doing. You have an agent, maybe a robot or a video game character, and it tries to accomplish a goal. When it does something that gets it closer to the goal, you give it a reward, like a treat for a pet. When it messes up, it gets a penalty. After millions of tries, it learns the best strategy to get the most rewards. Section 4, Inside the ML Toolbox. Okay, so we know how they learn, but what can they actually do? Let's look at the most common jobs we give these models.
So inside that supervised learning world, things usually fall into two big buckets. You got regression, which is when you're trying to predict a specific number, think how much or how many. And then you have classification, where you're trying to predict a category, think which one of these is it? Is it A or B, spam or not spam?
Predicting a house price is a perfect example of regression.
The answer isn't a simple category. It's a specific dollar amount that could be anything along a sliding scale. The model learns the relationship between stuff like square footage and the final price. And here we are back at our email filter. This is a classic classification problem. The model isn't predicting a number, it's just sorting an email into one of two buckets, spam or not spam. It's a clear-cut choice.
And for unsupervised learning, a couple of big tasks come to mind. First is clustering, which is literally just finding natural groups in your data, like that customer segmentation example. The other is called dimensionality reduction. It sounds super technical, but it's really just about simplifying things, like taking a huge spreadsheet with hundreds of columns and figuring out which 5 columns tell you almost the whole story.
Section 5, From Code to Cloud. Now, all of this sounds pretty intense, right? Like you'd need a PhD to get anywhere. But what's been so revolutionary is that you don't anymore. Making this technology accessible to everyone has been the real game changer. The best way to think about it is on a spectrum. On one end, you can just use powerful models that big companies have already built and trained for you. Dead simple. In the middle, you can take one of those models and fine-tune it with your own data. And then, way over on the far end, if you've got the expertise, you can build a whole new model from the ground up.
And this is exactly what that easy end of the spectrum looks like. With services like Google's Vision API, any developer can just plug into world-class machine learning. You can send it a picture, and seconds later, get back a list of everything it recognized: objects, text, even the emotions on people's faces, and you don't have to train a thing yourself.
Okay, Section 6. Let's bring this all home. How do these fundamental ideas we've just covered connect to all the crazy generative AI tools that are popping up everywhere?
Well, the big secret is that today's most mind-blowing AI is built on these exact same foundations. A large language model? Under the hood, it's just a gigantic supervised learning task, trained on nearly the entire internet to predict the next word in a sentence. The technique that makes them so good at conversation, RLHF, that's just our old friend reinforcement learning, using feedback from real people as rewards. And self-driving cars? Yep, they use that same trial and error reinforcement learning to get better and better at driving safely.
So, you see, machine learning isn't magic. It's a powerful framework for solving problems by finding patterns in data. But as these systems get better and better at learning from our world, it does leave us with a pretty fascinating question to chew on. In teaching machines to learn, what are we really learning about ourselves?
Today, we're diving into a really critical but maybe overlooked part of AI. How sure is it about the answers it gives us? I mean, getting a fact from an AI is one thing, but knowing how much you should actually trust that fact, well, that's a whole different ballgame.
So let's just jump right in. Think about it. We ask AI systems for pretty much everything now: medical advice, financial forecasts, you name it. And what we get back are these incredibly precise-looking answers. But behind that veneer of confidence, how sure is the model really? Is it like 99% certain, or is it closer to a 50-50 coin flip?
You know, there's this famous quote from the statistician George Box that just hits the nail on the head. All models are wrong, but some are useful. And that is the perfect lens for this discussion. See, every AI model is just a simplified version of our messy, complicated world. So it's never going to be perfect. The goal isn't perfection, it's usefulness. And a huge part of being useful is knowing what you don't know. Okay, so let's get into the core of this, what we're calling AI's confidence problem. Because let's be real, an AI that's super confident but dead wrong can be way more dangerous than one that just says, hey, I'm not sure. So how do we deal with this? Well, there's actually a whole field dedicated to it called uncertainty quantification, or UQ for short. Its entire purpose is to measure and communicate how uncertain a model is. It's all about turning that vague gut feeling of this might be wrong into hard, specific numbers. This is such a great way to think about it. We've all seen the weather apps say 70% chance of rain. But UQ gives us the context we desperately need. Is that a really solid 70%? Or is the model kind of shrugging its shoulders, telling us the real chance could be anywhere in a huge range, from 50 to 90%? You can see how, without UQ, that single number can be pretty misleading. All right, to really wrap our heads around uncertainty, we first need to understand how an AI sees the world. It's not in pictures or words like we do. Nope. At its heart, an AI sees everything as numbers. It all comes down to math, specifically linear algebra. So everything, and I mean everything, an AI processes gets broken down into these numerical structures. A scalar, that's just a single number. A vector is a list of numbers, like all the different features of a house you're trying to sell. An image becomes a matrix, which is just a grid of pixel values. And a whole video, that becomes a tensor, which sounds fancy, but it's just a grid with more than 2 dimensions. This right here is the fundamental language of machine learning.
And this brings us to this constant tug-of-war that happens when you're building any AI model. It's this delicate balancing act between 2 different kinds of mistakes, and finding that sweet spot is the key to making a model that actually works.
So what's this trade-off all about? It's bias versus variance. On one hand, you have bias. That's when your model is way too simple. It makes these broad assumptions and completely misses the real patterns in the data. We call that underfitting. On the other hand, you have variance. This is the opposite problem. Your model is too complex, so it starts paying attention to all the random noise in the training data instead of the actual signal. That's called overfitting.
Here's a perfect picture of what high bias or underfitting looks like. See how the data points clearly follow a curve, but our model is just a simple straight line. It's too rigid, it's completely missing the bigger picture, so its predictions are going to be way off. So the goal, the sweet spot, is to find a model that is just right. You want one that's flexible enough to capture that underlying curve, but not so flexible that it gets thrown off by every random little data point. It finds the signal hiding in the noise. And here's the other extreme, high variance. Look at this wiggly line. The model is so complex that it's twisting and turning to hit every single data point perfectly. But it hasn't actually learned the pattern, has it? It's just memorized the noise. A model like this is useless because the second it sees new data, it's going to fall apart.
Okay, so we get the problem, this whole balancing act. Now for the fun part. How do we actually solve it? How do we build models that can tell us how much they know or don't know? How do we quantify that maybe? One of the most powerful tools in the toolkit comes from a branch of statistics called Bayesian methods. And the key idea here is pretty revolutionary. Instead of spitting out just one single best guess, a Bayesian model gives you a full range of possible answers, a whole probability distribution. It's designed from the ground up to deal with uncertainty.
And the way it works is actually super intuitive. It basically just mimics how we learn as humans. You start with a prior belief, sort of an initial guess about something. Then you get some new data, some new evidence from the real world. You then combine your initial guess with that new data to form an updated, more informed belief, which we call the posterior. It's just a formal way of learning from experience.
Now, Bayesian methods aren't the only game in town. There are other really clever techniques out there. Things like sampling methods, where you basically run a model thousands of times with slightly different inputs to see the whole range of possible outcomes. And then there are ensemble methods, which I think are cool. You train a whole team of different models on the same problem. If they all agree on the answer, you can be pretty confident. If they're all over the place, well, that's a big red flag for high uncertainty. Okay, so we've been deep in the weeds of stats and math, but let's pull back up. Why does any of this actually matter out there in the real world? What are the consequences? Well, in high-stakes situations, knowing your uncertainty isn't just a nice to have, it's absolutely essential. I mean, think about medicine. An AI that confidently misreads a medical scan is a disaster waiting to happen. What you really want is an AI that can raise its hand and say, you know what, I'm only 60% sure about this one. A human expert really needs to take a look. The same goes for predicting if a bridge might fail or managing billions in financial markets. Sometimes the most valuable thing an AI can say is, I don't know. And that really is the bottom line, isn't it? A truly trustworthy AI doesn't just give you an answer. It gives you the answer, and then it tells you how much you should believe it. That ability to quantify uncertainty is what separates a cool tech demo from a reliable, professional tool you can actually depend on. So I'll just leave you with this final thought. The next time you use an AI, the most important question to ask isn't just, what's the answer? It's, how sure are you? Because at the end of the day, the most intelligent systems aren't the ones that pretend to know everything. They're the ones that are smart enough to know what they don't.